Um, Here is our June 15th, 2022 meeting. Let's get into it. All right, so TLDR highlights. I'm going to go over a progress report of iteration 5 from June 1st to June 14th. Is that correct? It is. Yes, yes, yes. Documenting free functions. I discovered that all of our free functions, even though we were doing a good job of documenting them, weren't actually getting looked at through Doxygen. So I'm going to go over how you fix that. I'm going to go, and the majority of this entire talk, majority of this entire discussion is most going to be around the poll handler, polling functions, the new 3 universal utilities such as timeout utility, poll utility, and delayed utility. They are very much akin to write and read, where you should be able to write and read to many different objects. Same thing with timeout, poll, and delay. Then I also have like a little bit of a planned update to embed ITC. It's small, but it's a bit of a change. And then why introduce embed poll handler? So why is this thing even a thing? Why am I even going over it? So before we go into this, let me go over the progress report for last iteration. So not gonna lie, we've had really well for the first 3 iterations were solid. A lot of work done. That was fantastic. The 4th one, not so much, but there was one big discovery between me and a couple other people, which is that the stubs did not make any sense, so we eliminated those. So at least we got rid of a whole bunch of extraneous work, but not too much work was done here. But at least we were able to figure out something that would remove a lot of work from us. Iteration 5 had a lot of stuff on it, but we really didn't get there. Sarah did a great job of getting her work in, but everyone else, we were all behind for whatever reasons. Including myself. I had quite a few things that I threw onto myself, and I did not really get to those. And I'll get into that detail after this meeting is over, when we chat about like just some other moves that the project is making. But yeah, so a lot of these are going to be moved over to the next iteration. I would say one thing in particular is that, at least on my side, a lot of these I've decided not to actually make example projects and to simply have them be like provide a driver saying, hey, if you want to learn how to make a good driver, here's our actual driver that you should look at. For example, for peripheral driver, I want to use the ADC driver because it's nice, sweet, short, simple, and it gets across all the points I want to get when it comes to how to develop a peripheral driver versus making what I did before with SJC Dev 2, where I provided a set of examples, but they're all dummy examples. So you can follow them, but they're kind of confusing because it's made up. So that's a thing. And yeah, so that's kind of what happened when it came to last iteration. So this one's gonna be even more packed. Probably gonna eliminate some of these that don't really make as much sense, but a lot of the ones like from the group in between here probably get moved over. And I'll have a conversation with a few people if they want to remove themselves from a couple assignments as well. So yeah, that's pretty much what happened for iteration 5. Another little update, if you guys had not seen this, the iteration for early launch has actually been moved to iteration 11, so it's August 24th to September 6th. We still have quite a few iterations before we get there, but hopefully we can nail a lot of these things and get them through. And then the late launch is now iteration 14, which is October 5th to October 18th. So that got moved over by an iteration. Hopefully we don't have to do that. Hopefully this will be the last time we have to do that. But yeah, so that's that. Let's get back to the slideshow. Okay. So the first item here. Oh, and if you have any questions or anything like that, feel free to just ask. Documenting free functions. This one's nice and simple. Basically, in order to get Doxygen to look at free functions, you need to add the at file description at the top of the file. Otherwise, only classes and structs get brought in. They're the only ones that get checked by Doxygen. So Khalil, will work on adding all these things to all our files and fixing up whatever documentation we have there. Everything's well documented. Sometimes there's a little bit mistakes here and there, like maybe there's a typo in some of the names, and we didn't notice it because we just assumed Doxygen was doing what it was supposed to do. And that's what I did until at one point I realized that something was missing, and then I was like, okay, this is not working. And this is what I've discovered. So whenever you're making a new file, and this is mostly going to be holding free functions, make sure to provide a block like this in that file. If it's an interface file, you can omit doing that just because it's kind of redundant and the interface is the only thing that's in there. Therefore, it will be picked up by Doxygen. Any questions about this one? Oh, and if you're wondering what that looks like, it looks like this. So here's the utility file for the counter. just put like file util provides utility handlers for the counter interface. You can literally copy and paste that because it's probably going to be the same thing for insert whatever interface you're working with. And then you have all the other stuff here to help you out. So yeah. Okay, moving on. Embed poll handler for polling functions. So the definition is basically here, using poll handler, that's the type, is equal to boost leaf results bool and takes no arguments on the input. So it's basically just saying that we have a function, can either return an error type or can return a bool, true or false. I'm still in debate on whether or not what the behavior should really be for a poll handler. So if you have any ideas by the end of the meeting, please tell me. But I think looking over a couple of examples and how it's used will give you an idea about how it's supposed to operate. Well, I wouldn't say examples of how it's used, but like situations in which it could be used. So a poll handler signals to a procedure that a condition has been met and that it should either bail out or proceed to another operation. The most common version of this would be timeout. Let's say you're running some operation and you don't want it to take too much time because you want to make sure you do other work. You want to use the poll handler. Usually a version of that takes a duration of time, and then you keep calling that function until eventually the duration of time has elapsed. When that has happened, then you know, okay, we've exceeded this amount of time. We need to now, throw an error or do something else because this thing's taking too long or whatever you need to do. So the behavior, as it stands right now, is each poll handler must have a condition in which it returns true or false. It returns true if the condition is met. Otherwise, it returns false. A poll handler must never return false after returning true, and can also return an error if an error occurs during the execution of the poll handler. So basically, you wouldn't put a while loop around this unless you're trying to delay or something like that. But normally, you would do some work, and at the end, you would then go, okay, whatever the poll function name is, let's just call it poll parentheses, and from there, if it returned back false, you know that, okay, the thing has not timed out yet, we can continue going, or has not finished its condition. If it returns back true, we know the condition has been met. If it returns back an error, you should probably just bubble up the error unless you want to handle it yourself. So those are the three situations that can basically be returned from the poll handler. And this is basically used for timeout detection, delaying execution, or signal detection. Any questions on this? Cool. Here are two of the utilities. We have timeout utility on the left and poll on the right. Timeout returns an embed poll handler callable object. So to give a little bit more credence to what that is, this could either be a lambda, or it could be a function object. And those are pretty much the only two things that will really slide for libembeddedhal and for C++ in general. Because if you sent over a free function, well, that usually can't be stateful. Usually having that thing be stateful is a bit complicated. So usually they'll return back callable objects. I'll show you a couple of examples after I go through the definitions here, or the other things here. So timeout has an overload for counter and a duration. And basically they do the same thing. The condition that they're waiting for is that the time elapses to a certain point. How they operate is very different though. Counter just tells you what the current count is, and that's it. It just counts up one by one until eventually it overflows and then continues count up. Timer, on the other hand, you give it a callback and you tell it when you want it to execute, and it'll execute it at that time. So in the case of counter, what it does, it takes the duration, takes its current time, and takes the time in which the timeout was created, and then subtracts the current time by that time. And when that time difference is greater than the duration of time, then it says, oh, our timeout has hit. So basically, if my duration is, let's say, 5 seconds, and I started at 1 second from t equals 0, and then it's 2, I know the difference is 1. If it's 3, the difference is 3. Is 2. And then keep going until eventually you hit 6. And once you hit 6, you subtract them. Now you can move on. Timer basically just waits until that function gets executed, and it flips a flag, and that's how you know it's done. Poll is very similar, except in this case, poll is not time-based. It is some other condition, such as serial and length. So in this case, we have a embed serial, and we're basically waiting until the number of bytes in the serial buffer has hit a certain number, or has exceeded it. And in the case with interrupt pin, you can give it an interrupt pin and a trigger. So you set up the interrupt to trigger on a particular condition, and when that particular condition occurs, it sets a flag, and that's it. That's done. And like I said before, the whole idea with timeout is that it should always return true after the first time. So each one of these actually should fit that model. Any question about the timeout utility or the pull utility? Okay. Ooh, that's an extra slide. Should not be here. So I'll move past that one. Delay utility. This one does exactly what you think it does. Stops execution of a procedure for a determined set of time or until a condition is met. Delay uses the return pull handler from timeout or signal to operate. So if you were to actually, you could actually potentially pass a serial interface or serial object to delay and then give it like amount of bytes you want it to wait for, and then it'll go and figure that out for you. I will say though, one thing I forgot to mention when it came to pull is that there is a potential update to serial because there's one other function that needs to be added to it, which is capacity. Because if you try to ask for, let's say, 100 bytes, and the buffer for it, the DMA buffer for it, only can support 10 bytes, you will never fill, and that will delay forever or never time out. So that's actually not a good thing. So there might be some added things in there to check for that kind of stuff. Overloads for delay are as follows. You have one for counter, timer, and serial. It does exactly what you think it would do. But just one little note is that delay is dangerous because it can lock up the system if a condition is not met. For counter and timer, as long as those are not misbehaving, those should work just fine. It's really serial in the signal versions of this. Oh, and I'm so sorry. I put the word signal here when it should just say pull. It was meant to say that this is a signal variant of the delay function, or like the delay function. Yeah. If a particular condition never gets met, like you're supposed to receive 10 bytes from a Wi-Fi driver or from a GPS module, you never get them, then you're stuck. Or if they're corrupted. So yeah, so that's delay. Next up.
Question.
Yes.
So, dumb question. So when you said earlier that timeout should always return true, but here, if for example, I have a timeout that returns false, would that be the only time that it triggers a delay request?
Timeout should return true when its condition is met. Returns false if it has not been met. So it'll return true or false depending on that condition. In this case, delay internally will create a timeout object and just pull on that. We'll just check on that until eventually the timeout turns out to be true, and that's when it stops delaying. That's when it kicks out of the delay function and does its own thing.
So the delay is always there at the moment that the function is timeout function or pull function is called.
Yeah, it'll stop at that point and then wait until it's finished.
Got it. Okay, thanks.
So yeah, so if you have like, let's say you want to delay you give it a counter and then you give it a time duration of like, let's say 1 second, it'll internally use timeout for actually doing the real heavy lifting, but it'll just really just wait for that 1 second. The reason why I bring this up, the reason why these things actually get handled underneath is that I want to make sure that when we develop this stuff that we look at pull handler as being fundamental, because it really is. For anything that needs to delay or stop or pause or kind of wait for something to happen, you should be using a pull handler versus having delay write its own implementation for how it should handle timeouts and that kind of thing. So basically it's code reuse is what we're looking for, and that's why delay kind of uses timeout, and this is supposed to be signal there. I'm trying to change that right now. Sorry, not signal, supposed to be pull. Present. So, yep. Any other questions? Okay.
Nope.
All right, so planned update to embed I2C. The main difference is that we're going to be adding in the pull handler as another argument to the I2C object. The additional function is basically there so that if you ever have, it's only really there for whenever you have a particular device that can clock stretch. That's really the only time you ever need to kick out of I2C. I2C is always controller driven, meaning that the MCU that's doing all the communication, provided that it's set up as a I2C bus controller, will have full control over the clock and will never need, if you're going to write, let's say 10 bytes to an object, to a device. If you're going to write 10 bytes to a device, that amount of time is pretty determinable. If you're going to read from it, it's also determinable. It does not become, you can't determine it once the other device chooses to clock stretch, meaning to hold the controller from actually being able to escape the I2C transaction while it does its own work. So because of that, really this is only really necessary when you have clock stretching available. But because that's a thing that's quite common, we need to make sure we support it. In most cases, I am pretty certain that the poll handler will just be an infinite, something that just simply returns back false all the time to basically prevent it from ever bailing out early. And to Matt's point back in the day, I remember we having a discussion about whether or not we should have a timeout or not. I said that you don't need it because the controller supports this, but then, and I thought clock restriction wasn't going to be that big an issue, and then I realized that it actually is an issue we should actually support being able to bail out if that ever happens. So that's pretty much that's the situation when it comes to the update to embed I2C. All right, next up. Now, the big part here is why even introduce this whole embed poll handler thing? So there are 3 problems in particular. There's actually a lot. I'm pretty sure there's actually other problems that this actually solves, but here are the big 3 that have been on my mind. So last iteration, we actually spoke about how, I believe it's last iteration, we spoke about how the global timer, counter, clock, whatever, they were removed and thus the driver cannot use them to delay, to determine current time, or to poll for a duration of time. The solution here to this is to provide a universal polling type, which is what we have interfaces that need the capability to determine timeout conditions to basically take this type as an input parameter, specifically probably using std function. The reason why we do std function for this is so it's polymorphic, so you can use free functions, lambdas, and functors. If you don't know what a functor is, I'm actually probably going to talk about it in a little bit so you guys can kind of get an idea of how this should be done. And then finally, provide utility functions for generating these handlers so that they are consistent in their behavior. There's consistency in their behavior. So that is pretty much this little situation here. When we remove the global timers, now all other drivers don't have anything they can rely on in order to get, to delay, in order to get current time, that kind of stuff, which is still on purpose. That's not a bad thing, actually. By not having a singular global counter, timer, or clock, you now have that flexibility on what you want to pass as the poll handler. Before I go any further, I actually want to say that the poll handler is an abstraction, or it erases the implementation details about what the condition is and leaves that all up to the developer. You don't have to worry about if it's time-based or signal-based or whatever it is. All you know is that here's a function I've been given to that whenever it flips from from false to true, I know I need to do some work. Normally, your driver should actually have a definition for how that thing should behave. Like, oh, give me a time-based thing. It should not exceed this, blah, 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 that kind of thing. So that's one particular situation that we need to support. Number 2, well, how does one unit test polling and timeout behavior, especially without a global reconfigurable clock? So before, you were able to actually set what the global clock was, or uptime and delay functions were. And in this case, actually, we get better control over this because there's one big issue. With the previous code, if you actually change the global clock, then you need to make sure to change it back. If you don't change it back, then now all other tests down the line could be broken because of this. And if you did not change the global timer and you had something that waited like 10 seconds and it actually waits for 10 seconds using the, and I'm assuming, and right now I'm talking about host tests. On host tests running on your laptop, it'll actually will wait 10 seconds. So your actual tests will be a lot longer than they really should be. We don't really want it to delay for 10 seconds. You want it to simply run as long as however you want to run. So this becomes another dependency injection site where test code can control the behavior of the poll handler, as well as also spy on how often it gets called. So that's the second little problem that we solve here. Then finally, this one's a doozy and kind of long. So I'm and this is the most important part of this. And if you look back at the launch the launch I don't know why I can't think of it. Spreadsheet basically is the way to put it. The project site. You'll see that my actual assignment was timeout handler or timeout timer. And the idea of timeout timer was that you give it a duration of time and it would tell you how much time is left from the time it was constructed. Now I'm going to talk about this. I'm going to kind of glue those 2 parts together. So let's consider we're trying to build a Wi-Fi client driver, basically something that can allow us to go out to the internet, do fetch a website and bring it back. I use that because this is literally a real life example that I had to deal with quite often. We'll talk over serial. So every time you have a query, you have to wait for a response OK back. Literally, the device will return back the response OK. Now, these responses can vary in the time they come when they get returned, and that really depends on how much work the ESP has to do, or if the ping is very long, or if the reception is really bad. There's a whole variety of things that can go into play that can cause the OK response to take some time. It also depends on what type of command you're sending to it. So let's say that you have a driver that has to perform some work. Well, it doesn't really matter what that work is, and you say, I want to give you 10 seconds to do this work. And it requires you to send 3 messages and also to get 3 responses back. Sending messages is super fast, but getting responses back is slow. Or it could be slow, depends. You have to ask the question of, well, how much time do you give for each response? You could do like, well, let's say that the last one takes a while and the first 2 are usually pretty short. So I can give 3 seconds to the first one, 3 seconds to the next one, and then 4 seconds for the last one. So it's kind of evenly distributed. The only problem with that is that when you do this, let's say that the second one actually ends up taking a little longer than 3 seconds and bails out early. Well, that's unfortunate, because if we had actually played the whole thing through and, let's say let the third actual message come back with a response, it might have been really quick. So overall, we actually didn't go beyond 10 seconds of time, but we still bailed out too early. That's not okay. So the answer to solve this is that the amount of time you give for each response, to wait for each response, is the amount of time that's left. So if the first one takes only 100 milliseconds to delay, then now you have 9.9 seconds to do the second message and the third message. So you can give that time to each one of these. Now, why is this particularly a problem? I mean, that solves the issue that we were talking about before, but in terms of efficiency, space, as well as also time, it doesn't really work out so much, because consider the amount of operations it takes to basically take that particular time duration and then decide on how you're actually going to write your code in order to handle it. Normally, you would probably just have some setup code in order to, well, what ended up happening before is that you would actually either pass the timeout handler through, which actually does what we're doing, so it's not too big a deal. But a lot of times for other interfaces that take a duration of time, they'd have to construct their own timeout handler and then do the work of figuring out how that's supposed to operate for them. And without a global timer, they have to kind of figure that out on their own, which may require them to utilize a timer that's built into the MCU, or try to infer time using some other aspects of the driver. There's a lot of ways that this can get really complicated and kind of ugly. And the depth in this example is only 2. When you get to 3, 4, 5, of depth of like timeouts over timeouts over timeouts, this can become quite complex. You spend a lot of operations just simply setting up your handling of did we time out or not. So the real solution here is to use a pull handler, because after you construct them, they're ready to go. All the context about the amount of time or the condition that they need is all set up at construction, and you can simply call the function and get the condition, whether or not the condition has been met or not. Simply passing it through will give every single API call, every single bit of code, the ability to know whether or not that timeout has ended. And that will save a lot of operations, because now we've just reduced it down to a single call and passing the function object through. But yeah, so that's kind of the idea of the pull handler. I'm going to show you guys a bit of the code a bit, just so you can kind of see how some of the stuff kind of gets written. This is not done yet. This is not brought in. I can actually show you what the timeout code looks like, or the delay code. So here you have delay. You give it a counter. You give it the amount of time in nanoseconds. There's a function called create timeout. I'm actually going to return that back to timeout. We can have a discussion afterwards if you guys think that it should stay as create timeout. We'll go there in a little bit. You give it p counter and you give it p duration. And now we just keep calling the timeout until eventually it either returns back an error, which is what the boost leaf check does. Check to see, it will return back an error if there's an error that occurs. If not, it pulls out the Boolean true or false value. And once it returns false, this continues. If it returns true, it escapes, and then you return back a successful error object. And then we have some code here in order to actually handle the timeout timer. It's a bit complicated, and I'm actually going to move this from, actually this should, I'm going to move this from using lambdas into functors. And functors are basically just any class that test functor that supports operator parentheses, which looks really confusing because it's really supposed to look like this for the operator for this, kind of like when we do operator plus. But in this case, the operator is parentheses, so you have another parentheses for the actual function. It's, yeah. So that's all a functor is, just a class that has an overload or a definition for the parentheses operator. Lambda is pretty much the same thing, really. So that's pretty much it. This will hopefully be put in soon so that you guys can all look at this and kind of get an idea of how it's supposed to work. And the thing that I'm trying to prevent is what happens here. Oops, that's a little bit big. Here we have this timeout timer. And we have to then supply for this read until a get time left. And then here we have another get time left. And each one of these will basically create their own, well, they won't create their own timer because they don't really need to. They don't have other operations below them. But let's see if we can find that one. Oh my goodness, where is it? Yeah. It will have its own, actually has its own waiting function to see if a particular operation happens in a particular amount of time. So it takes that timeout duration and runs with that. And if it gets any deeper, then you have more and more nested timeout timers everywhere. And it's a lot of extra stack space is not necessary. It's also a lot of additional computation that is not necessary either. So that's pretty much timeout timer and why it's important and why we're going to be using that going forward. Any questions? Because we're pretty much done here. Any questions? Cool beans. All right, so that's pretty much it for this meeting. And I will see you guys in 2 weeks. Well,